Hi everyone, good morning, good evening, depending on where you are logging in today. Um, Welcome to this second session of our webinar today. We had one in the morning European time, and now it's the morning American time. Let me just pause this one, otherwise I hear myself. So welcome to this webinar where we will discuss the project we did on Twike, which is a German three-wheeler, electric vehicle three-wheeler, where we cut the drag by 29%, which is really dramatic, and with a focus on highway speeds. That means you're burning about two-thirds, almost three-quarters of your energy just to push the air out of the way on the highway. That means if you can slash the drag by 30%, you can increase the range by more or less 20%. Of course, depending on your driving cycle, this may differ, but 29% drag coefficient reduction, that's what we are going to discuss today. A short note on the agenda. So we're going to introduce Airshipper first and Twike, then dive into the details of the drag reduction. Afterwards, we are also going to have a look at the cabin flow, which is the flow inside the car, just to improve the comfort of the passengers, to make sure that we have an evenly distributed outflow out of the different openings, the different vents, and so on. We're going to have an open look at the cost of the project so you can actually judge for yourself whether this could be useful, and we're going to have a Q&A session at the end. So please drop your comments and then I'll take the time afterwards to answer your questions. So first of all, the introduction. What is Airshapper? So Airshapper is the company that I founded in 2015 after I had been running simulations, both FEA, so finite element analysis, and CFD, so computational fluid dynamics, for about 10 years. And I wanted to make it more accessible compared to the traditional way of running CFD simulations, which is a valid way if you're a large company doing this day in, day out. And the process traditionally involves acquiring a CFD license, which is typically around 30,000 to 100,000 US dollars or euros for a single license. Then you have to buy the hardware, which can range anywhere from 5,000 euros to another 100,000 euros, depending on how quick you want your simulations to finish. And then you need an expensive person with a lot of background and experience in simulations to operate the software, to set up the simulation, to wait for a license, to process the results afterwards, to make images, and so on. So it's very expensive, and it's time consuming. Still valid if you want to do this day in, day out, use your license 8 hours a day or 10 hours a day. But if you want a quicker workflow, then Airshipper is a very interesting alternative. It's highly reliable. It doesn't come with a license cost, so we just charge per simulation. Um, that means you can already run a single simulation at Airshapper for just 50 euros. A very simple tryout simulation. You can just do it for 50 euros and get started. If you want to do it properly, then we have a number of bundles that you can acquire. They come with credits, which you can spend on both the simulations, but also on our expert consultancy. So you have a solution for your software, hardware, and expertise all in one single bundle. We can work directly with non-watertight models. Prior to the webinar, I had sent you a white paper a white paper on the Tesla Cybertruck that we analyzed using our platform without a single modification to the 3D scan that we got of that car. And the 3D scan was not watertight at all. It was composed out of hundreds of components with loads of non-manifold edges. We can just work with the model that you have today without any time spent on closing the gaps and the holes and so on. So this really dramatically speeds up your workflow because it can take anywhere from a few days to weeks or even 2 months, for example, when you have to prepare a full car or a train, for example, to run CFD simulations. Every simulation you run on Airshapper will feature adaptive mesh refinement, which means the computational mesh, which is kind of the resolution, like a digital photograph, of your simulation will start with the mesh, which has already been automatically generated and refined as you get closer to the surface, the typical way you would generate a mesh manually. Then we run that simulation, And once the simulation has converged, we will then look at the flow field. We will analyze the gradient of the pressure, the vorticity in the flow, and then refine the mesh locally where it's most relevant for your flow in the weight, for example, that you see here in turbulent areas and so on, and make the best possible use of the cell budget that we have available for your simulation. So when we talk about a 10 million cell mesh, it's usually the equivalent of maybe 20, 25 million cells that you would generate manually using conventional techniques without adaptive mesh refinement. And last but not least, we work for many OEMs across the world, and they require very tight security measures to be implemented. So we have done so. Our platform runs in the cloud with all of the security measures that we inherit from the Google infrastructure. We only use local servers here in Belgium and the Netherlands. We work on the NDA for those customers who want that. All data is kept private by default, and I will dive into the details later on. So, short summary, this is all available on our website as well. But just to summarize, you can really dramatically accelerate your time to market. Instead of working for months to get your model ready for CFD simulations, you can just work directly on the models you have, which also means you can pull the aerodynamic development phase way further upstream in your development process. So, as soon as you have your first sketch, however rough it is in 3D of your car, your drone, your train, your sports car, or whatever application you're working on, you can already run an aerodynamic simulation, get insights, and take it into account right from the start. Whereas in the conventional process, you would postpone it because you don't want to optimize that model the whole time. And once you start doing aerodynamics, it's usually too late to make dramatic changes and you end up with a compromise. So integrating aerodynamics right from the start is one of the key components to end up with better performance and faster time to market. As mentioned, it's a very cost-effective solution. There is no license fee. Every euro you spend on Airshipper directly translates into credits that you can use for both simulations and for consultancy. There's no investment in hardware, there's no specialist needed, and we have flexible pricing plans. Industry proven accuracy. So if you check our website, we have tons of validation cases where we use our code across various disciplines, whether it's internal flow through pipes, whether it's propellers, whether it's cars, drones, trains, trucks, and so on. The exact same code delivers results which can come within just a few percent deviation of the measured wind tunnel data. So if you have any questions, just head over to our website, click on cases, then on validation, and you'll find more information there. And of course, also refer to the paper that I have sent to you prior to the webinar. We have an effortless user experience. You don't need to rely on an expert. You don't need to hire someone with expensive skills. We have a fully automated workflow, which allows you to set up simulations within just 5 minutes, and you don't have to prepare your CAD geometry. We're active in automotive engineering, which is the topic of today, but we also work on aviation applications, aircraft, eVTOLs, which is electric vertical takeoff and landing aircraft, new concepts, drones, very big topic. And we also work on hydrodynamics, where we work on hydrofoils, ROVs, which is remotely operated vehicles, so submarine kind of vehicles with remote control, kind of drones underwater, and so on. In terms of security policy, as mentioned, you can find all of the details on airshipper.com/security, where we detail how we implement the latest security standards to comply with the requirements of the OEMs that we work for. If you still have any questions, let us know, and we can explain in detail how we handle your data, how it's kept private, how all of the IP always remains with you, and so on. So please do reach out if you have any questions. Send an email to security@airshipper.com. Just a few interesting applications. Today's topic is the car, the Twig, but the exact same code is being used for other applications. Just a few weeks back, this video was released, and you can find all the videos on our website or our YouTube channel. This video was released on the world's fastest drone. It's an official Guinness World Record, clocked at around 580 kilometers per hour. Really cool. All done with Airshipper, the aerodynamics. So check it out if you're interested in that one, and stay tuned because there's more coming in terms of high-speed drones developed with Airshaper. We also won this competition on designing the best possible propeller, so hydrodynamics in this case with rotating geometry, where we linked our platform to KCs, which is a German software platform that can parametrically change shapes. We linked our platform, built an AI model together, and then found the best possible solution and won the competition and increased efficiency by 58% in that case. This one is the land speed record card. There's many different classes, but within the class of 1000cc engine, this person, Superfast Matt, a very cool YouTuber, broke the record at Bonneville at the Speed Week, and he set the record to 270 miles per hour on just a 1 liter engine. So really cool, also done with Airshaper. We support the 4 times Pikes Peak winner, Robin Shute, both for his side projects where he designs cars for others and races them up the hill, and also for his new upcoming record car for Pikes Peak. In terms of truck regulations, our platform has the capabilities to run simulations which comply with the regulations of Vecto. So Vecto is a tool that you can use to quantify your emissions and your gains in terms of efficiency when it comes to trucks that go on European roads. So if you're working on trucks and you want to run certified simulations, we have direct connections with certification bodies like TUV and so on. So please do reach out. This is the paper that I sent you where we reverse engineered the Tesla Cybertruck, and our simulation results were very, very close to the claimed values, and lots of insights there. Our YouTube channel is filled with cool videos on topics like we went to NASA to visit the Ames Research Center, the Armstrong Flight Center out in Mojave Desert, where the coolest X-planes were developed, first plane to break the barrier of sound in level flight, and so on. So if you're just genuinely interested in aerodynamics and you want to learn the basic theory, real applications, how to design drones, cars, and so on, please do check out our YouTube channel. In the context of today, we also have the Aptera, which is also a three-wheeler and also very much focused on efficiency. Very different layout. This one has 2 wheels in the front, one at the back, which is the opposite of the Twike that we'll be seeing today. Nevertheless, this one is also very efficient, was optimized using our morphing simulations, and also features solar panels. And then this morning we had actually the designer of this car in our webinar, Adriano Raeli. He designed the entire bodywork on this custom Lamborghini. The design brief was to make it as fast as possible. We redid the entire bodywork. Every single body panel was modified to reduce the drag. We cut the drag by around 27% compared to the donor car, which is a Lamborghini Huracan. And on the first test, the goal was to reach 420 kilometers per hour. On the first test, we actually reached 447 kilometers per hour. So stay tuned for more. Now, the topic of today, I'll stop talking about Airshaper. The Twike is, the Twike 5 actually, is the upcoming vehicle by Twike, which is a company which has already been in the market for many, many years, offering very cool concepts where you can pedal to go forward in very lightweight vehicles. In this case, the development involves an electric vehicle with a range of more than 600 kilometers, a top speed of up to 190 kilometers per hour, and an efficiency of a very high efficiency with a energy consumption of just 7 kilowatt hours per 100 kilometers, which compares to maybe a Tesla Model 3, which I believe is around 15, between 12 and 15 kilowatt hours per 100 kilometers, so dramatically lower than that one, and a weight of just 685 kilograms. So let's dive into the topic of today, which is how to reduce the drag by 29%. The first thing we did was to upload their existing design, which you saw here, which is just the design that you saw here. So they had a design which is already very detailed and then came to us for aero optimizations. And we wanted to know where we stood in terms of aerodynamic drag coefficient. So we entered the velocity, we selected a moving floor, which means virtually the floor is moving. And as you can see, the wheels were detected automatically, which means you don't have to go in to set the axis of rotation or define the radius. That's all done automatically on the platform, and the RPM is set automatically to match the driving speed of the vehicle. So literally, this is it, what you're seeing here. There's nothing else. You just select the accuracy after this, run the simulation, and about 2 hours later, you have your simulation results. Now, for the first simulation, we're going to analyze what we saw. And it was actually quite sobering because we were expecting a good drag coefficient, but then again, we saw quite a lot of flow aspects that were telling us that the drag coefficient of 0.311, which is quite okay, but not what we wanted, was actually being caused by a number of issues on the car. So if you go front to back, I'm just gonna zoom in on this headlight because this is really a nice feature to explain a number of crucial fundamental concepts on aerodynamics. So, excuse me, when the air hits a surface which is kind of straight up, like the nose of the car or the headlights, the pressure will build up. And the maximum pressure you can get here is what we call your stagnation pressure. So if the air comes to a complete standstill on the nose of the car or one of these forward-facing faces, um, it comes to a standstill and the pressure buildup is the highest. And from there, it needs to accelerate again and make its way out of that area. So in case of the nose, that means going to the top, to the bottom, left or right. In case of the headlight, that means probably going to the top and to the sides. But what happens is the air will hit the front face of the headlights, the pressure will pile up, then the momentum will actually change direction. You will have an upward momentum, and that means this sharp corner here between the front face and the top of the bonnet here is actually too sharp for the air to follow. So the air has too much momentum, it will jump up, fly up, and then only land further downstream on the surface again. So that means below that trajectory, you have a bubble of separated or detached airflow. So that means the air jumps across, and inside this bubble, you have air recirculating. So going back and forth, dissipating energy and reducing the quality of the flow that actually travels further downstream on the car. Now, you can also deduct this from what we call the surface friction. So this is the amount of friction that is generated by the air traveling parallel to the surface. So even if you have a perfectly smooth surface, when the air travels across a surface, there's always air sticking to the surface, and the velocity of the air on the surface, if you would zoom in with a microscope, is always zero, which is what we call the no-slip condition, even on a perfectly smooth surface. So if you have a green color, for example, that means the air is actually following the surface. You can tell also by these parallel streamlines here on the surface that there's nothing funny going on. But when you have air which is jumping across a certain surface, it actually goes through the air and it doesn't follow the surface anymore. And then you see these weird recirculation lines. And the quantity on the surface is blue, meaning that there is low surface friction between the air and the surface because the air is no longer following that surface. But you would maybe argue that's a good thing. That's lower friction means lower drag. Yes, that's true. But the friction component of your total drag on the car is just around 5 to 10% on a car, which means you may have reduced the 10% to 9.5%, but you have increased the other component of drag, which is the pressure drag, maybe by 5 or 10%. So when you see low surface friction areas, usually it's either an indication of stagnated flow, which is still attached at the front of the car, gets squashed against the nose and then spreads out again. That's not a problem. But if it's in the wake of a sharp edge, for example, this indicates separated airflow and is a warning for you or a trigger for you to look upstream to analyze why the flow actually separated in the first place. So this is a good example of pressure building up and then sharp edges disturbing the flow, causing separation of the flow and causing drag. So if we use that knowledge to continue our explanation, we can see that the headlights are a source of drag because the air needs to jump to the top, to the sides, and creates flow separation. We see a mildly similar effect around the front splitter. So the good news is that the splitter was already quite nice on the Twike. So most splitters that we come across are flat plates sticking out, which is the main purpose of a splitter, because what you do is you want to capture some of that high pressure on the nose, which is not just on the surface, it's here in the volume. If you stick out a plate, it's just like holding out your hand and scooping up some of the pressure which is acting on that plate, and that plate is attached to your car, so your car is being pushed down. That's the purpose of a splitter, at least on race cars. In this case, usually if it would stick out, you would have like flow separation around the sharp edge. This one already had like a nice round here, which is good. We have attached flow at the bottom. It's only at the sides here, around this sharp edge here, as soon as the flow tumbles around this one, that we saw some flow separation, small challenges here. And then we have this air deflector, which was an add-on part, added or connected to the bottom of the front splitter to actually divert the flow around the front wheel so that the wheel itself would be shielded, because the wheel itself rotates and has a very rough geometry, not in this simulation, but in reality you have your tire thread and so on, causing flow disturbances as well. One of the key problems with this car was this, what they call the potato shape. So Twike dubbed this the potato shape, which is this infinity symbol shape that you have here, which allows the wheel to just rotate left and right as you want to steer. As you can imagine, if you rotate this wheel to the left, it will be aligned like this. If you rotate to the right, it will be aligned like this. So you need clearance. And even though we're currently looking at a cover that will rotate together with the wheel to close this shape, most of the design optimizations were done for an open shape. So what we saw in terms of flow results is that as soon as the air hits the edge here, it separates, because there's no way that the air can just curve inside and follow the curvature. It separates, it has to jump this gap, then hits this suspension. We call it a SIBO suspension element, because the wheel is suspended from one side. It hits that element, then again comes across the gap here, and again hits the end of the gap, and again separates. And this translated into a very significant wake, traveling all the way downstream, not just causing drag on the wheel itself, but causing a lot of problems in the diffuser as well. Because this dirty airflow reduced the momentum of the air at the underfloor of the car. And you can see that there's quite a bit of height to this flow separation and this wake behind the front wheel. This traveled all the way down to the diffuser, where it's caused detachment, not just in the wake directly, but also spreading out across the width of the diffuser. So it's not just the wheel, it's the performance of the entire underfloor of the car that was heavily compromised by this design. Then we also saw some minor details like bolts holding the bottom plate to the car, some small gaps here at the bottom causing flow separation. Then we had the, let's say, the pockets for the windscreen wipers. So this was already nice. There was an area to tuck away the windscreen wiper, but it wasn't high enough, and some of the air was still hitting the windscreen wiper and causing flow separation. By the way, a short note on the resolution. This one was done, and the bulk of the design work was done at medium resolution, which is what we call our regular simulation of 10 million cells. We also have one of 1 million cells, very low resolution, and also one of 100 million cells. We ran a mesh sensitivity study, which means we would run simulations at 1 million cells, 10 million cells, 100 million cells, just to see when you get reliable convergence or stagnation of your forces in function of your mesh count. If you increase the mesh resolution and you see that your drag coefficient doesn't change much, then you can usually conclude, okay, we can make do with this resolution without spending all of our time and effort on the highest resolution. So the bulk of the work was done with our regular simulation of 10 million cells. So around the A pillar, we also saw that there's some flow separation. So an A pillar is always a challenging area on a car because you have a flat forward-facing windscreen and you have a side window which is actually parallel to the flow. So the air hits the front windscreen and then either goes via the top or via the sides, which means it tumbles around the A pillar and curls up. And this curl structure then moves upward all the way to the roof of the car, and in this case also collides with the mirror, which was actually quite close to the car. So very complex area to get right, and also a big source of noise. We're not going to zoom in on the noise, but we use our platform, even though these are steady state simulations, based on an acoustic analogy, we can make predictions on the biggest sources of wind noise, which in this case is definitely the mirror, which is also work that we do for other OEMs across the globe, in the US, in India, and so on, to quantify the wind noise that we see around the car to then mitigate those areas and reduce the noise to improve the comfort. Especially important for electric vehicles where the engine noise doesn't mask the wind noise as much. Then we saw that we have, well, the B pillars and geometries around the window sticking out. They weren't perfectly flush, so this caused flow disturbances, this one as well. And then we saw that the panel gaps were actually quite large. And sometimes you need these as a rain gutter or something else, but they were quite large, causing flow separation, mild flow separation in the boundary layer of the car on the roof. And this really disturbed the flow. The hinges were sticking out and so on. Then we had the wheels. The wheels, of course, have their own tire wake, which then joins the wake underneath the car. There's airflow being disturbed as these rotating wheels interact with the flow passing via the sides of the car. We had this very tricky area here where the airflow actually wants to curve around this wheel arch, but at some point this becomes too steep, and again the flow just maintains momentum and continues on a straight trajectory and actually separates. Now the problem is before it separates, it accelerates and creates a low pressure area on this area, just like on the rear, on the butt of the Audi TT, which was very curved in terms of geometry. This creates a suction effect, which creates both drag and lift on the car. So we had to optimize this area a lot. And that's it in terms of the existing analysis. So if I go back to our presentation, we wanted to know how to improve this design. And to that end, we ran a design advice simulation on AirShaper. Now, design advice is based on what we call, or what the industry calls, an adjoint simulation. An adjoint simulation is an extra simulation that you can run after you have finished your normal simulation. This new simulation will, based on a different set of equations, it will link your goal function, which in this case was the drag, it will link it to the movement of the surface. So it will tell you for each point on your surface, if you want to reduce drag, you should either pull the surface outward along the normal, which is the red area, or inward along the normal, which is the blue area, to reduce your drag. So if we have a look at some of these interesting areas, for example, the headlights that we were discussing, over here, the software is telling us this area is red. It means push the surface outwards. So what would happen? You would get like a bulge here. And this bulge here would actually fill that wake that we saw of the air jumping across. And it would provide a landing area or a guiding surface for the airflow to remain attached and then land further downstream. And the edge itself here, which is blue, according to the design advice map, it tells us move this inward so that your edge is less sharp and you actually round it off. So together, that means round off the edge and provide a smoother landing area for the flow. So the same happens here. So this is an upward angle, and then you have this flat area ahead of the headlights. Well, that's no good. The flow will separate here. So the design advice is telling us this is blue, push the edge inward, and behind the edge, pull the surface upward a bit so that it becomes more tangential with the rest of the flow. And like this, it's full of interesting design advice on how to change the geometry around the mirror to help guide the flow without losing too much energy. There's suggestions on actually how to push the wheel arches outward to create a jump across the wheel. Here we had these pillars sticking out. So if a pillar is sticking out, the design advice is telling us to actually pull the window outward a bit so to make it more flush with this edge sticking out and so on. We had advice on the air deflectors in front of the wheels, the air deflector in front of the front wheel, and so on. So all of this gave us great insights as to how we could improve the airflow. So we went to work and we started working on the nose, and we also ran morphing simulations, which is a feature which is available on our enterprise plan. The morphing simulation doesn't just provide design advice, it also implements this design advice. So if you look at this one, if you look at the nose of the car in this image here, you'll see that if I play this evolution, you can see that the nose is being pulled forward a bit, which was giving us a slightly more pointy nose, which was reducing the pressure buildup that we saw there. So that was one indication as to how we could reduce the drag. The second one was the front air deflector to shield the front wheel. As mentioned, it was an add-on part. If we look at the optimization there, if I play this one, you can see there's quite a dramatic change in geometry that our software provided. So afterwards, we were able to download these 3D files. Twike was able to import them and then replicate this shape and morph it together or blend it with their existing design constraints. So this optimization, again, hinted at how we could reduce the drag on this geometry. Then comes a very important one, which is the diffuser on the car. It's slightly more difficult to see on this one, but what was happening is we had a fairly straightforward diffuser, just an angled surface upward, which started to go up as soon as the hard point of the chassis was passed. In this case, the software was telling us, well, instead of using a straight line, it started denting the diffuser. So in the middle, it pushed the diffuser upward, which gave us an S curve actually for the diffuser, which means you're still pulling the airflow upward, but after you pull it upward initially, you flatten out to make it go horizontal again to recover some of the pressure loss so that you don't have this suction effect, which would actually generate drag on your car. And this has been key for future iterations on this car. And we saw a similar effect when we looked at an optimization on the roof of the car. So we had a downward slope convex curve, and the software was actually suggesting, when we looked at just the rear spoiler here, to give it a more aggressive downward curve and then a kick towards the rear, which is again this S shape, which allows you to contract the wake a bit more, but then you recover some of the pressure, which would otherwise lead to a suction effect and to drag on the car and also to lift on the car. So again, a very strong indication as to where we had to look for improvements. And then this one was also instrumental in optimizing the car. We wanted to optimize the splitter left and right of the front wheel, and surprisingly, the software was telling us, well, please pull up the front splitter. And that's, for many people, quite counterintuitive, because you would think if you push more air underneath the car, you would actually just increase the drag, right? Well, in this case, it was the exact opposite. Because pushing more air underneath the car, left and right, actually feeds more high momentum, high energy air left and right of that very difficult open front wheel area to then actually feed that energy into the wake to reduce the wake that we saw behind the potato, behind the front wheel. So this will be highlighted further down the presentation as one of the key features of the optimized design. Nevertheless, by tweaking the splitter, the diffuser, the mirrors to some extent, all of these small areas, well, large areas, but with limited freedom, resulted in a drag reduction of around 10%. We went from 0.311 to 0.28, which is already a very impressive improvement, but it was not enough. The goal was to go to 0.22, which is extremely aggressive, especially for a car with this layout. So we went to work. We teamed up with Voyager, who is a design agency whom we've known for actually more than 10 years now. They're also based in Antwerp, Belgium, where we are located. And we teamed up to tackle things in a much more dramatic way. So we sat together, we kicked off with a brainstorm where we highlighted all of the hard points which were not to be modified because a lot of the car was already designed and carved in stone. And some areas were still up for discussion, like the nose geometry, the rear of the roof, the body panels on the sides, and so on, not the wheels. So we went to work coming up with ideas, analyzing whether we could optimize the tailgate, if we could close the wheel actually, whether we could extend the car, and so on. And we started brainstorming, putting post-its up the physical board, up the virtual board. We looked at the hard points in the chassis to know where we could start curving upward for our diffuser, if we could extend the side flanks behind the rear wheels. We drew inspiration, obviously, from existing cars like the Chiron with an open end to draw air through the car. Looked at other highly efficient cars like the Mercedes Vision EQ XX, the BMW i8, and so on. We considered extending the car, which we did in the end, the length of the car, changing the roof geometry. We started playing around with this dual front splitter that we saw that was showing a lot of potential. We played around with the idea of internal flow channels, which is something very dear to my heart because that's how I got started. This is the car I designed 15 years back based on such principle, which was also patented. So really cool that this came up again. Looked at the long tail concept, which is typically a way of reducing the drag to just extend the shape of the car, just like you saw on this Mercedes concept, this one. It's also like an extendable or at least a very long tail. Then we looked at channels to feed air to the wake behind the front wheel, which is this sketch here. We looked at making a convex nose instead of a concave geometry there. We looked at shielding the headlights or maybe just adding like a small gurney, like a small windscreen to kick the air up and around the headlights. We thought of integrating the front mirrors into the bodywork. We looked at reducing the panel gaps, changing the spoiler and later on the entire roof and so on. We started implementing this in more detail, implementing this together with all of the details of the bodywork and the chassis, structural components, the hard points. Looked at other concepts again. So all kinds of brainstorm sessions. And then we came to the conclusion, well, it's really hard to tell the difference or to quantify the effect of every single change if the car is already this detailed with the panel gaps, with the air deflectors, with the headlights, with the mirrors, and so on. So we were struggling to know whether it was a problem of the base shape or a problem of the detailing of the car. So what we then did is to reduce the entire car to just the most minimalist design possible, which was what we call the soap model. So you can imagine if you hold a piece of soap, use it 20, 30 times, it becomes nicely rounded. Well, that's what we did to this car virtually. So we came up with a very clean model, which allowed us to quantify the drag of this model without any fancy features, just the base elements like the front wheel without even the potato shape, the windscreen deflector, and that's it. Windscreen wiper deflector, and that's it. And this resulted in a drag coefficient of 0.262. So then the question was, is this the best we can ever do and every single detail will increase the drag, or can we actually optimize the base shape to reduce the drag? So we set out to optimize the base shape, which is not an easy task because if you want to have a drop shape, which is aerodynamically very interesting, you want to have like the widest point at the front of your car and then taper it inwards towards the rear. That's aerodynamically the most interesting shape. And here we actually had the opposite. We have the passengers sitting relatively far back in the vehicle, and we have a nose sticking out quite far ahead. So we had the opposite. We had a wedge going through the air and leaving a wide wake at the rear instead of a very thin wake at the rear. So we started optimizing this shape again using the shape optimization techniques. We implemented the side channels that we saw to feed high energy air around the front wheel. And what we saw is that this brought the drag down to 0.248, which was a dramatic improvement and a very, very nice and welcome signal for us to focus on this area. So instead of having this closed nose, which was very wide and low all the way to the sides of the car, we now had airflow being channeled at high speed underneath the car with a very smooth curvature, and the wake was very, very small now on the front wheel. So that was great news. But then we were wondering, well, are we just going to destroy everything? Because if we feed high energy air into the potato, we might actually make things worse again. So we put back the potato shape, and then we saw that drag indeed went up again to 0.266, which is where we started with the potato shape, with the soap model, but this time this was with the potato shape already included. So we were back at the same level, but with more realistic details included, which was a good sign. So more energy to actually reduce the entire problematic area here. Then we looked at the diffuser, again, ran plenty of optimization studies on all kinds of accuracy levels, different geometries, and so on. And again, we saw that the software was putting this dent upward into the diffuser, creating this S shape. So again, we started playing around with the diffuser. We looked at the entire roof this time, or at least the last third here, not just the spoiler. Again, ran an optimization, and this time we again saw this S shape, so this convex concave combination to reduce the size of the wake and then get this pressure recovery, again showing loads of potential. Then we ended up iterating massively. So what I showed you now is just the tip of the tip of the tip of the iceberg. This is an Excel sheet that Twike kept, and it doesn't contain nearly close to all of the simulations, but just to show you, we went to a convex nose where we integrated the front air deflector all the way into the nose geometry itself and blended it nicely with the side air channels going to the sides of the car. We added side fins to actually grab more air and feed it underneath the car. We optimized the potato shape. We added nice rounds here because the air would just enter the potato shape, go out again, enter, go out again across these sharp edges, which would create flow separation every time it would cross the sharp edge. So we created nice landing areas for the air to just land on the shape, leave it again, and so on. We added a firewall to reduce the turbulence inside the front wheel area. We played with the potato shape itself to contract it a bit, to slim it down. We added wheel deflectors ahead of the rear wheels to just push the air away from the tires so that the tire wake doesn't pollute the diffuser as much. We worked with, we optimized the wheel deflectors extensively, first as an isolated assignment, and then later on we started combining this with many other features on the diffuser, like sidewalls to keep the tire wake from spilling over into the diffuser wake and so on. More on that later on. We experimented with different channels for the diffuser. It was a very interesting exercise because there are hard points in terms of the let me just zoom in. In terms of the chassis points, the hard points, we also had to work with a trailer connection point because this car can actually tow a trailer. The suspension was actually going through the diffuser channels at some point, so we worked with moving parts to actually shield that with slot gaps to move the suspension. We looked at adding covers to the wheels themselves, which would move together with the wheel to shield or control the tire wake. We also looked at static walls connected to the chassis and the bodywork instead of connected to the wheel. We looked at elegant or funny shapes to actually shield the trailer hitch. This is again the side wall, but then a static one to keep the air inside the wheel, to keep the spillover into the wake area. Different mirror designs. We morphed the mirrors. We looked at different suspension elements. We looked at different types of strakes, which are vertical baffles, to actually control the flow direction in the diffuser. We looked at very simple diffuser shapes. We looked at very complex shapes with two separate channels on both sides of the car. We continued with many more concepts, optimized outlets, these flanks behind the rear wheels, and more. All of these isolated areas were coming together into one nicely morphed, organic, complete picture of the car, which is really nice to see. We started optimizing the nose together with the deflector, together with the side channels, together with this flow, nicely feeding air underneath the car, together with the side flanks on the car. So it's a very organic looking shape, which goes far beyond these isolated 2D optimizations that you sometimes see on cars. Different shapes for the headlights, different geometries to push the air across the windscreen wipers, and so on and so on. Just an endless list of iterations, optimizing the geometry, the angle to shoot the air downward into the wake behind the rear wheel housings, optimizations of the roof, how far we should extend, to which length we should extend. Sorry, can I drink something? Analyzing just how far we should extend the car. Different shapes for the rear of the car. The cutoff kind of looks like a Zagato for those people into cars. Um, we looked at openings inside the bodywork to ventilate some of the high pressure air that we would see on the car. Um, endless optimizations, and as you can see, this is not even half of the list. So this one continues. We worked with vortex generators to energize the airflow before it enters the diffuser to maintain attachment. This is a special diffuser channel which actually was a bit deeper because the chassis was a trapezoid shape, and then this channel would sit right in between that existing chassis. So it very much was an exercise of optimizing within existing constraints, different geometries for the diffuser. This is the movement of the wheel. So the wheel, as it moves up and down, it has a certain envelope which moves up and down. Very cool concept on this car. Again, diffuser optimizations, even the hinges to open the boot or the trunk of the car were optimized and aligned with the local airflow and so on. So just an insane amount of work. Even in top view, we worked with this S-curve to optimize the car and to contract the wake without creating too much suction effect and so on. This is just list number one. List number two is also over here. So endless number of iterations. If I go back to our list, the result is that we actually achieved the 0.22 drag coefficient that was set out as the goal. Just to show you the final model, if you look at this one, this is now the nose, which is one organic blended shape where we have a convex shape here to guide air via these channels, high speed into the wake, into the underfloor. This one just morphs nicely around the potato shape. Then the front air deflector is actually integrated. The wheel itself got its own deflector or cover, let's say. It's still an asymmetric airflow because the suspension is only coming from this side. The airflow traveling downstream is actually flirting with flow separation, but it's not separated airflow. It's slowing down, but it's not stalling. Then you have this very organic combination of the rear wheel deflector combined organically with the sidewall to keep the tire wake under control, combined with the most aggressive part of the diffuser, which here featured this S shape going upward into the diffuser. So here you can see the diffuser going up and then flattening out again. And then the central part, which is sitting right below the hard points of the chassis and covering the trailer hitch, again featuring this S curve. So one complete area connecting the air deflector, the sidewall, the diffuser, the central part, the trailer hitch, and so on into one nice organic shape, which is really, really nice to see. We have very limited flow separation in other areas. So again, this S curve featured on the top of the car. We have the hinges here, and the hinges themselves, they are actually not aligned with the driving direction, but aligned with the local flow direction, which is not 0 degrees. It's maybe 5-10 degrees angle of attack and so on. So that's also very interesting to just look at your local flow pattern and align your hinges with these flow lines so that they don't act like a sail or a wall, but just are aligned nicely with the flow and so on. So tons and tons of optimizations. We have some local flow separation left around body panels, which were already designed. Small bit here, but that's about it. So really, really, really cool. It has been fantastic to work with Twike on this. They have been extremely flexible and open-minded to question everything which was there to come up with this extraordinary design. So again, hats off to the Twike team, hats off to Voyager for all the 3D modeling together with Twike. Now, a few side notes before we dive into the internal flow. If I load this project, a few other things you can do if you want to further optimize your car is to, for example, optimize the ride height. So we can automatically add tire compression. If I add a tire compression, you can see that the car actually sinks into the floor because the tires get cut off. You don't have to do this in CAD anymore. You can change the ride height at the front to maybe 40 millimeters lower, and this will automatically adapt the ride height. If I just exaggerate, you'll see that the rear of the car goes up. So this is all possible within Airshipper if you have an enterprise plan. And you can also set your radiators. So radiators are an important part of aerodynamic drag as well, because you need to force air through them, which costs energy, which can be translated into drag. So if you model the radiators as a solid block, we can actually model the flow through the radiator. And once the simulations are done, you can just have a look at those elements and analyze whether your radiator is being used properly or not. So if I just have a look at this one, you can see that the flow is mainly going through the bottom part of the radiator on this one and not necessarily through the top part, which means if you optimize the ducting towards this radiator, which in this case is a side air intake on this area, and then the ducting goes down, the air gets trapped at the bottom, and that's why it gets forced through mainly the bottom of the radiator. If you optimize the ducting, you could really make do with a smaller radiator or improve the cooling if you improve the ducting. So definitely something worth looking at. If we then look at the cabin flow, as promised, we were also going to look at the internal flow. This is the HVAC system, or at least part of it, where Twike applied a flow rate at the inlet and pressure openings at the outlets inside the cabin. So this is the flow rate where we provided a flow rate of, let's say, 200, or yeah, this is not realistic, 20, 30 liters per second. And then this flow makes its way through the channels. And then we could actually analyze just how evenly distributed or actually unevenly distributed the airflow was in the beginning. So if you click on the inlet, and this is all automated, you just need to click inlets and outlets to set up the flow, and that's it. If I then in the results click the inlet, I can automatically see the streamlines, I can see the distribution of the flow lines, see where the highest momentum airflow is going, see where you have pockets of recirculating air, and so on. And if you click the outlets, you can just analyze the flow rate on the outlet, on this one, and see that there's just a 10-20% delta, maybe in this design, and it's still ongoing. And if you click on the inlet, you can also analyze your pressure drop, which is then useful input for your fan selection. Because you want to know for a given flow rate how much pressure buildup you need, and once you know those key parameters, you can start selecting your fan. And then this is to defrost the window, for example, so you can actually check where the airflow is coming from leading up to each individual opening. So that's also really insightful just to see which areas you can still optimize. This, for example, is a pocket of air that is still featuring some energy loss, so that could be optimized. If I then continue to the project cost, here too, we got the approval to be very open about this. Let's say the entire project for the Airshaper simulations, so including the brainstorming, the sessions we had, 2 sessions per week, brainstorming, updating each other, our consultancy, all of the simulations, the 280 simulations, the morphing, everything included, was a budget of around 50,000 euros for the aerodynamics part. Now, usually you would spend this amount on just buying a license, which means you haven't done anything yet. You don't have a computer yet, you don't have a person working on that project yet, and you don't have someone running, setting up the simulations, processing the simulations, and you don't have an expert yet. For that same budget of just a license, we did the entire project. In terms of 3D modeling, the support that we got via Voyager, let's add another, let's say 50,000 euros. For 100,000 euros in total, we took this car from a drag coefficient of 0.311 all the way down to 0.22. And of course, it really depends on how much design freedom you still have. But if you let us do our thing as a standalone team, we can really come back with the wildest improvements. And the sooner you involve us, the more room there still is to optimize the design. Now, you don't have to jump to that budget straight away. We have different pricing plans. Obviously, Twike used our enterprise plan, which allows for all of the accuracy levels, 1 million, 10 million, 100 million cells, all of the simulation types. We saw just normal analysis. We saw this design advice, the blue and red color map, and we saw the automated morphing. And we also saw the use of wheels, radiators, and so on, which are all features which belong to the professional and enterprise plan. For students and hobbyists, we have a discovery plan, which includes 25 credits, which can only be used to run the low resolution simulation at 1 credit per simulation. We have a professional plan, which comes with 100 credits, which allow you to run both basic simulations, 1 credit for 1 million cells, and also regular simulations, which is what we use for the bulk of this project, 10 credits per simulation for 10 million cells. Plus, this plan and the enterprise plan allows you to use the credits to get our expert consultancy at 10 credits per hour, which means we will jump on a call, analyze all of the results together with you, and based on our experience with race cars, hypercars, drones, EVs, and so on, give you our input on how we think you can improve your design. So if you just want to try out Airshaper, introduce it within your team, within your company, the professional plan is a very, very cost-effective way to just run maybe 8 regular simulations and have 2 hours of consultancy to discuss your existing designs. Then Q&A. I'm going to hop over to the Q&A. So if you have any questions, please drop them in the chat, and then I can actually follow them right here. Let's see. I'm not seeing any questions. Maybe something went wrong on my end. Maybe I didn't enable this. This morning we had quite a lot of questions. If you have questions, let me know. I hope I can still pull up the questions. It's a bit of a mystery to me why it is not working this time, while it was working actually earlier. Okay, my bad in terms of the questions. So if you do have questions, just reach out to me at info@airshaper.com, and then I will reply to your questions personally per email. You can also reach out to me on LinkedIn, where we also post content on drag reduction, on drone design, and so on. And if you have any questions other than that, you can also always drop a comment on this webinar on the YouTube video, and then I'll get back to you as soon as I can. So Really, thanks a lot for joining this webinar. I hope it was insightful. And if you have a project, even if you have an existing workflow for CFD simulations, just reach out if you want to see what we can do for your company, for your project, for your car, or for your other application to further cut the aerodynamic drag in a record time. So thanks a lot for watching. Have a fantastic morning, evening, and hope to be in touch with you soon.